Be right with everyone. Stay as a participant. Testing. Let me see. Okay, there it is. Okay. All right, looks good. All right, gentlemen, let's see. So, welcome. Hope everyone had a great weekend. Okay. Let me see. So we're entering the home stretch. Like we really don't have a lot left. Let me just pull up a calendar real quick. So today I just updated the attendance from last Wednesday. So I know we had that attendance quiz. Uh, I probably will go through and check the attendance records. If I see that people have maybe 4 or 5 or more unexcused absences, then I'll probably be reaching out to you. So, just to make sure that you intend to stay in the course, because sometimes when you get many unexcused absences like that, then you can get booted. And at this stage, if you get booted, it might be difficult to get back in. Anything, because some guys have just been completely MIA, and it's like, okay, are you trying to finish? So I don't know. We'll kind of play it by ear. But if you kind of fall in that 5 or more category, then you either just want to kind of just try to keep an eye on your emails or just reach out to me directly and say, hey, I know I have an excessive amount of unexcused absences, but I intend to finish the course. Please don't drop me. Something along those lines, so then I can at least try to, on some level, get you on my radar. So it's like, okay, I know he intends to finish. Yeah, because some guys are just like they disappeared. I got to track you guys down and check on you, make sure you're okay. Let me see. So I want to say next week is Thanksgiving. So this week, today, we only have 2 sessions remaining. I know normally on Wednesdays we do a homework session, but I think what we're going to do is shift it up a little bit this week. So today we'll do section 3.1 exponentially functions, and then on Wednesday, instead of going through the homework, we'll go ahead and do the last section, which is like section 6.4, system of equations in 2 variables. So that'll be on Wednesday. So then we can start reviewing for the final. That'll give us 3 days of review in preparation for the final. So then next week on Monday, the 25th, we'll review exam 1 to all sections pertaining to exam 1. And then we'll be out for the rest of that week for the holiday, for Thanksgiving holiday. So, that's a great time to, for students, I would imagine 2 objectives. One, kind of get caught up on any late assignments. That's a great time to like finish out stuff. So, if you're going back and submitting old assignments or missed assignments or late assignments and you're trying to boost your overall grade, my recommendation, prioritize your exams first. That's where you're going to get the most bang for your buck. If you scored less than 95% on an exam, it doesn't hurt to try to boost the score. You get unlimited attempts. The system is only going to take your highest score. So you have nothing to lose and everything to gain. Once your exams are wherever it is you want them to be, then I would prioritize the homework last, all right? Because the homework is going to be a lot of work for minimal points, right? So the main thing is get those exams in order. The idea or the goal is that, like, as we go into the final, idealistically, once you submit the final exam, you should be done. You shouldn't have assignments that you're trying to submit past the final. Let me see. So yeah, that Monday again we'll review exam 1. The rest of that week we're off for the holiday. I think the school closes at noon on that Wednesday. I'm just gonna let you guys go. So we don't even have, we're just gonna take that day off just to match my other groups. So then we have the holiday, then we come back. That last week is that first full week of December. So that Monday, December 2nd, we'll focus on exam 2. And then that Wednesday, I think it's December 4th, we'll do exam 3 along with these 2 additional sections. The reading period is that Thursday and Friday, December 5th and the 6th. And then the final exam week is that second full week of December. It's basically that Monday the 9th through that Friday the 13th. Right now, again, you can anticipate for me to host your final. So what that means is that the final should become available on that Sunday, December 8th at 11:11 a.m. You can access it until essentially that Friday the 13th, right? That's the hard deadline for all assignments, okay? So just kind of be mindful of that. You want to, once we hit that Friday the 13th, then everything is going to lock out. So you want to do the best you can to try to be done before then, okay? Because once we hit that, that's it. Can't think of anything else. Okay. So I'll mention this. So there may be an extra credit opportunity in the form of your overall My Math Lab score, provided I can do it. Like usually what I'll do is like I'll take everybody's overall My Math Lab score and scale it so that it counts as 10% of your overall grade. Provided it doesn't skew the grades too much, then I'm willing to do that. But if I notice that it just boosts the grades too much, then I won't do it. I think also this group or this section has the lab of Dr. Lamar, so just kind of keep that in mind. Hopefully you've been, in communication with her and following her instructions. Remember, her portion counts as 10% of our overall grade. Okay. All right. So I can't think of anything else. Let's go ahead and get the party started. Again, whatever we don't do together, I do expect you to kind of use my pre-recorded lectures to, fill in whatever we don't do together. Okay. Let me grab this. Ooh, yeah, and if you have questions, feel free to either unmute yourself or type in the chat or the Q&A. Do you have a question? I don't think so.
I said, hold on. I said, when you need to wake you up?
Unmuted. Oh, there we go. I think we're good. Yeah. So again, if you have questions, feel free to either unmute yourself or type in the chat or the Q&A, and we'll make sure to get those questions answered. Okay. So we have this is our first of 2 auxiliary sections. So we have chapter 3 on this chapter focuses on exponential and logarithmic functions, but we're just going to be working on section 3.1 exponential functions. A few objectives here: 1, define an exponential function; 2, graph exponential functions; 3, develop formulas for simple and compound interest; 4, understand the number e; 5, graph the natural exponential function; and 6, model with exponential functions. Okay, let's minimize this for now. So function f of this form, f of x equals a to the x, where a is strictly positive, or a is positive and not equal to 1. This is called an exponential function with base a and exponent x, and the domain is all reals. So in the past, you may have seen things where you have like, x squared, 7x to the power of 3. Those are essentially power functions, right? You have some variable raised to some non-negative integer power, right? And so we kind of explored that. So here, now we're going to switch those roles. Instead of the variable being the base of the power function, now the variable is going into the power. It's going to become the exponent. And so we're going to explore, what happens when we have a positive base not equal to 1 raised to some variable power, right? We're going to be exploring those, okay? And again, we call this an exponential function with base a and exponent x, okay? Let's see. So given these exponential functions, we're basically evaluating. I think I'm just going to leave this as an exercise. I feel like you can handle this. I'm just going to leave this one because I think you can figure it out. But you definitely want to make sure that you can generate those results. So you have the results there. So we're going to let that be. So in graphing the exponential function, right? We want to graph this guy. So we're given f of x equals 3 to the power of x. And I think for this one, I just went on and gave the y values, right? So normally we would choose the x values, choose several values of x, and find the corresponding y values. So we would plug them in. In this case, it'd probably be a little bit easier to kind of work backwards, starting with 3. So then if we said 3 to the power of 3, so that's 3 times 3 is 9, times 3 gives us 27. And then when x is 2, so that's 3 squared, which is 3 times 3. So then that's 9. 3 to the power of 1 is 3. Essentially, any real number other than 0 to the power of 0 is a 1. Let me think. I'm curious. Let me think about that. It should be 1. Let me see. Because now I'm thinking about like a negative number to a power of 0. I just want to see something in my calculator. Let me see. I think so. This. We just close on these. We don't need this. Let's go here. Like, what if we did a negative to the power of 0? I'm just curious. Clear. So like if we did negative, let's do negative 5 to the power of 0. Okay. All right. Well, that answers that debate. Let's do 0 to the power of 0. I just want to make sure that one too. Okay. Yeah. So yeah, any real number other than 0 raised to the power of 0 is going to be 1, right? Okay. And then when x is negative 1, so a negative exponent is a fraction. All right. So if we have 3 to the power of negative 1, that means 1 over 3. All right. 3 to the power of negative 2 means 1 over 3 squared. 3 to the power of negative 3 means 1 over 3 cubed. Okay. So now we have this table with a set of ordered pairs, or x's with the corresponding y's. Well, when we plot the points, we get an image like this. So this image on the right is the general shape of an exponential function. With minimal to no manipulations, this is the shape that our exponential functions are going to take. Notice as it goes off to the far left, it's approaching a horizontal asymptote, which is in this case is going to be the x-axis. So again, as long as we don't move it or manipulate the base function, the x-axis serves as a horizontal asymptote going off to negative infinity. There is no vertical asymptote for this guy, right? So every x to the right is accounted for. It grows rapidly, but you know, it looks like, I know it's tempting to be like, oh, there's a vertical asymptote. There's no vertical asymptote, right? So like when x is 5, you can find the corresponding y. When x is 10, you can find the corresponding y. When x is 1,000, you can find the corresponding y, right? No matter what x you choose going to the right, each x is accounted for, okay? So the domain, if we're looking at this image on the right, again, the domain is going to be the very left to the very right. So all the possible values that x can take on. Again, for an image like this, the domain is going to be all reals, right? Can anybody tell me what's the range of this guy? What's the very bottom to the very top? Yeah, feel free to either use the audio or just type it in the chat. I'm just curious. Anybody tell me what's the very bottom to the very top? How far down does this graph go versus how far up does the graph go? Right. Right. So the very bottom, yeah, 0 to infinity, the open interval is correct, right? So in the chat, someone put the open interval, basically using parentheses on both ends. It gets infinitesimally close to 0, but it doesn't actually reach 0, right? Because of that asymptote. So the range being the very bottom to the very top is going to go from 0 to infinity. Okay, so those are some properties. Yeah, so that's the meat and potatoes, okay? So we saw the first one was an example of what we call exponential growth. I think our base was larger than 1, you know, the base of the function was larger than 1. So now here, notice that the base of our exponential is between 0 and 1, right? Okay, so that's a little bit of hint, or hopefully you can do a little bit of foreshadowing. So then again, we just chose several values of x. Namely, we chose from -3 to 3, and we find the corresponding y's. And in this case, it might be a little bit easier to start with the -3. So then if we have 1/2 to the power of -3, again, the negative exponent causes it to flip. So instead of becoming a half, it flips to 2. So then it's really 2 to the power of 3, and that's where the 8 comes from. 1/2 to the power of -2 is really 2 squared, which is 4. 1/2 to the power of -1, which is just 2. 1/2 to the power of 0 is 1. And then 1/2 to the power of 1 is itself. 1/2 squared is a quarter, and then 1/2 cubed is an 8. Okay. So again, we have our table of values, our x versus our y's. We're going to plot our points. So this is an example of something that we call exponential decay. because as we trace it from the left to the right, it's always decreasing. We still have our horizontal asymptote, right? Is the x-axis. There's no vertical asymptote, so every x is accounted for. For every x, you can find the corresponding y. Yeah, so the domain is all reals. I think this has the same domain and range as the previous. It's just the previous was exponential growth or is an increasing function. As we trace it from left to right, the previous was going up. This one is exponential decay, or in other words, it's a decreasing, a monotone decreasing function, meaning that as we trace it from the left to the right, it's always decreasing. Okay. All right. So some properties there. So more properties of exponential functions. So given the exponential function where the base is positive and not equal to 1, like we just saw in the previous examples, the domain of an exponential is going to be all reals. Every x is accounted for. The range of an exponential function is going to be the open interval from 0 to infinity, okay? The entire graph lies above the x-axis, okay? Yeah, that's fine. Let me see. If we consider f of x plus 1 over f of x, that's going to be a to the power of x plus 1 over a to the x, which is the next line, which essentially boils down to a. So in other words, what this is showcasing is that for each unit increase in x, y increases by a factor of a, right? So every time we increase x by one unit, y increases by a factor of a, okay? So whenever our a is larger than 1, the growth factor is a. Because the y value increases by a factor of a for each unit increase in x, then we're going to say that f is going to be an increasing function. So again, when the base of the exponent is larger than 1, the exponential function is going to be an increasing function. So the graph is going to rise as we trace it from the left to the right. As x goes off to the right, or x goes off to the positive infinity, y goes to positive infinity. As x goes to negative infinity, y gets closer and closer to 0. Right? Okay, so that's the first graph that we looked at. And then when the base of the exponential is between 0 and 1, this is called a decay factor, is going to be a, because the y value decreases by a factor of a for each unit increase in x. So for the decay factor, every time every time x increases by 1, y decreases by a factor of a. So again, when that base is between 0 and 1, the function is going to be a decreasing function. So the graph is going to fall as we trace it from the left to the right. As x goes off to negative infinity or to the far left, y goes to infinity. As x goes off to positive infinity or to the far right, y tends to 0. Each exponential function f is 1 to 1. So let me see, did we talk about that? I don't think so. But 1 to 1, maybe we did. I don't know. But 1 to 1 just means that every y corresponds to exactly 1x, all right? And so the way we show algebraically that a function, so 1 to 1 has there are 4 statements. Let me just say this because I'm not sure that we specifically talked about this. But yeah, so inverse functions, right? So 1 to 1. 1 to 1 means that these 4 statements are going to be, we can use interchangeably. A function is 1 to 1 is the same as the function passes the horizontal line test, is the same as every y corresponds to exactly 1x, is the same as the function has an inverse, right? So those, I'm going to say that one more time, but those 4 statements we use interchangeably. So whenever you see 1, you can flow to any of those other 3 as needed, right? So a function is 1 to 1 is the same as the graph passes the horizontal line test, but that's the same as every y corresponds to exactly 1x, and that's the same as the function has an inverse, okay? And so an inverse function undoes the original function, right? So we'll get more into that a little bit. So so algebraically, in order to show that a function is 1 to 1, so if we consider 2 distinct exponential functions where you have a to the power of m and we set it equal to a to the power of n, then through algebra we should be able to show that m equals n. If we start with the left and then we finish with m is not equal to n, then the function is not 1 to 1, right? But again, to show algebraically that a function is 1 to 1, we start with the left expression, we finish with the right. Okay. In other words, it's f of m equals f of n. We finish with m equals n, right? So then again, f has an inverse. Okay. So a little bit of a mouthful, but it flows once you kind of get into some examples. The graph of f has no x-intercepts, right? Because it lies entirely above the x-axis. So it never crosses the x-axis. No value of x will cause the exponential function to equal 0. The graph of an exponential function is a smooth curve, and it passes through these three critical points, right? So when we're graphing exponentials, we have these three key points that gives us the general shape of the graph, whether it's exponential growth, exponential decay, whether it's been inverted vertically, right? So, we're kind of tracing these three key points when x is -1, when x is 0, when x is 1. And again, that gives us the general shape of our exponential. Again, those will just come out naturally as we kind of start looking at some of these graphs. From 4.3 and 5.3, we conclude that the x-axis is a horizontal asymptote for every exponential function of this form. Again, without manipulation, the x-axis serves as a horizontal asymptote. And the graph of y equals a to the negative x is a reflection about, so we flip it horizontally, right? If we think about the general shape of an exponential, on the far left, it starts infinitesimally close to the x-axis. It passes through the point 1, 0, and then grows to infinity. Then if we raise it to a negative power, it flips it horizontally, right? So then we have exponential decay. Okay, so that's essentially what's going on there. Okay. So again, that was just an overview of properties of exponentials. Don't stress too much about that. I just wanted to kind of like plant the seed in your psyche and your subconscious on some level. As you work examples, this stuff will just naturally start to come out. You don't have to exclusively sit and like memorize that. It'll just naturally come out the more examples you work. So then we have a few more definitions. The interest rate is the percent change for the use of the principal for a given period. The interest rate denoted by R is expressed as a decimal. Unless stated otherwise, the period is assumed to be 1 year. That is, R is an annual rate. The amount of interest computed only on the principal is called simple interest. So when we're talking about interest, our lowest form of interest that we have is simple interest, which is I equals PRT. The simple interest I on the principal P at a rate R expressed as a decimal per year for T years is given by this. Again, this is called our simple interest formula. The interest equals the principal times the rate times the time. So this is our lowest form of interest that we have. Okay. So Anita has deposited $8,000 into a bank account for 5 years. A simple interest rate is 6%. How much interest will she receive at the end of the 5 years, and how much money will be in her account at the end of the 5 years? Okay, this one isn't too terribly bad. It's fairly straightforward. So the first challenge is, making sure that we're using the right formula. Okay. So simple interest, I'll just put it here. Like we said on the previous slide, I equals the principal times the rate times the time. So for part A, they ask for the interest. Again, one of my mentors will say every time you use the formula, write it down. That helps you to remember it. So the interest equals the principal times the rate times the time. Okay. Our principal is $8,000. The rate is 6%. So the rate has to be expressed as a decimal. So we do need to convert 6% to a decimal. Let me do this off to the side real quick. So if we say, let's use this color, 6%. The percent symbol, you can look at it as per 100, all right? So then this is going to be the same as 6 times 1 over 100. Okay. So if we divide 6 by 100, we move the decimal to the left 2 places. 1, 2, right there. So we divide it by 100, right? So 6% as a decimal is 0.06, okay? But the percent symbol, you can look at it as per 100 or 1 over 100. So then you would say 6 divided by 100, move the decimal to the left, and that's how you get that number, okay? So 6% would be 0.06. The time said was 5 years. Okay. Let's see. 6 times 5 is 30. So it's a 324. There's a 10. 1, 2, 3. And then this, is that right? 2,400. Okay, so let me actually just use my calculator since I have it. I was practicing my mental math, but for whatever reason I'm not confident. Let's do 8,000 times 0.06 to 2,400. Okay. Times 5. Yeah. Okay. All right. So look, I just kind of want to recap the mental math that I was doing, what I was testing out, right? So I knew that there was like 1,000 here, right? There were 3 zeros there. This was like 0.01, right? And I kind of kept that in mind. So I said 6 times 5 was 30. So then there was an extra 10 in there. And so instead of working with 30, I just worked with 3. So then I said 3 times 8 was 24, right? Then if I account for that 10, I added a 0 plus the 1,000 was 3 more zeros. And then the 0.01 means you move back by 2, and that's how I got that. I just thought it was interesting, just an alternate way. You don't necessarily have to do all that. You can use your calculator, all right? It was just kind of playing around. Anywho, so the 2,400, right? So that's the interest earned. Okay, so that should be part A. It worked that time. I kind of want to try it again and see how many times I can get it to work. But we'll have other opportunities. Okay, so then for B, we want the future amount is going to be her starting amount plus that's not an official form, plus the interest earned. Okay, so she started with what, 8,000, and she earned the 2,400. So 10,400. Okay, well, I guess not too bad. All right. 2,400, 10,400. Okay, you guys are looking good. Oh, wait, let's check the chat. 0 to infinity. Okay, let me see. How is that possible? I think we answered that question. All right. Oh, how much? It's 5 years, all right? Let's just recap real quick. Yeah, so she started with $8,000. Every year is earning 6%, right? For 5 years, all right? So, let me see, 10% will be 800, so 1% will be 80. 80 times 6 is $480 each year, or for the first year. And you kind of have to, it's kind of weird because you get what do we get? 480 for that first year. So then at the end of the first year, she has the 8,480. But then at the end of the second year, you got to recalculate it based on that new amount. So you're basically doing that each year, right? Simple thing is, again, for simple interest, 8,000 times the 0.6 times the 5. Yeah. Okay. Not bad. All right, so compound interest, right? This is going to be the interest paid on both the principal and the accrued or previously earned interest. Interest that is compounded annually is paid once a year. For interest compounded annually, the amount after 2 years is given by this. I kind of want to bypass this one because this one only applies the interest once per year. I'm gonna skip this. This one is in my recordings. If you just want to see it worked out, I'm gonna bypass this one because this is the one I want to get to. The compound interest formula. This is the same as the previous. It's just that in the previous, the interest is only applied once per year. Well, this one, the interest is applied several times per year, right? Okay. Grab this. So this is our compound interest formula. So A is like our future amount. P is our principal or our starting amount. The rate is the annual interest rate expressed as a decimal. And N are the number of compoundings per year. Okay, so what that is how many times the interest is applied in 1 year, and then T is the number of years. Okay, so this is the one that, the previous formula is pretty much the same as this one. It's just that in the previous one, N was equal to 1. So I'd rather you just put your energy into this one instead of the previous one. And when I say previous one, I mean I'm skipping this one right here. The compound, this is annual compound interest. That's a derivative of this guy. Okay. All right, so let's see this in action. So say $100 is deposited into a bank account that pays 5% annual interest. We want to find the future value A after 1 year if the interest is compounded annually, semi-annually, quarterly, monthly, and daily. Okay, after 1 year. Okay. So this is compound interest formula. Let me see. So the future amount is going to be P times 1 plus R over N to the power of NT. And again, you don't really have to commit this in memory. You just need to know what's the proper formula to use in a lot of these instances, okay? So then let me see. So the $100, I think we're trying to solve for A, the future amount. Our starting amount is $100, okay? The rate is 5%, so we have to convert that to a decimal. Now, for instance, for number 1, if it's annually, that means our N equals 1. Okay. For number 2, if it's semi-annually, that means our N equals 2. For number 3, if it's quarterly, our N equals 4. I'm trying to leave some space. For number 4, if it's monthly, that means our N is 12. And for 5, if it's daily, that means our N is 365. Okay. So it's basically the same formula over and over with the changes in N as such. So what I'm going to do, I'm going to use my trusty dusty rusty. The only thing that's changing is N. So I'm going to go to my Y equals. Let me see my principal. My principal is what, $100 times 1 plus the rate. 5% is a decimal, is 0.05 divided by, now since the N is our variable, it's what's changing, I'm going to put it in as X to the power of the time is what, 1 year, so 1 times X or just X. Okay. So then I'm going to quit. And what I'll do, variables, you can call on the function. We want to evaluate this when X or N is 1, we get this answer. All right. So after 1 year, we've earned $5. Right? $5. Anyway. So the result here, so after 1 year, and again, only thing I changed, I just plugged in when X was 1, or my N was 1, everything else is staying the same. So let me see, A of 1, sorry. That's not right like that. But the result here was $105 for the first one. Okay. So then, now I'm just going to evaluate this when N is 2. Should be a little bit more. So what, at 6 cents, 105 and 6 cents. Come on. There you go. Thank you. Now we want to evaluate it when N is 4. And 9 cents. And then what, when N is 12. Let me see. 105 and 12 cents. And then 365. And what, 13 cents. You should notice something. The more compoundings we do in a year, you should notice something about these results. Okay. 105, 6, 9, 12, 13. All right. So hopefully in the previous example, you notice that the more compoundings we did, the more money we were making. And we did it like, okay, in a year, if we applied the interest once, how much would it be? If we applied the interest twice in a year, how much would it be? If we applied it 4 times in a year, how much would it be? If we applied it every month, how much would it be? If we applied it every day, how much would it be? So then the limit to those number of compoundings would be this guy, which is called continuous compound interest. So if the interest was just always being applied, how much would it be? So then whenever you see the word continuous compound interest, we use this guy. I like to remember this one as PERT. That's just how I remember it. But the future amount A is going to be the principal times e to the power of RT, where e is just a function in the calculator. It's the exponential function in the calculator. Okay. 8,000. Oh, did I put 10,000? It should have been 10,400. Let me make sure I put the right thing. Yeah, 400. 10,400. Maybe I said 10,000, but it's 10,400. Okay. So here we're asked to find the amount when a principal of 8,300 is invested at 7.5% annual interest rate compounded continuously for 8 years and 3 months. Okay, 8 years and 3 months. So we saw continuous, right? So we're going to use the future amount. So we're going to do PE to the RT. So let's see what we're given. What's our principal? Find the amount when a principal. So our P is 8,300. Rate 7.5%. So the time, it says 8 years and 3 months. We need that to be in years. So 3 months, and if it's 12 months in a year, 3 over 12 is a quarter, right? So that's 8.25 years. Right? Okay. So then our future amount $8.25. That should be 8,300 times e to the power of 0.075 times 8.25. Here. So 8,300 e 0.075 times 8.25. Okay. $15,409 and 83 cents. $15,409 and 83 cents. Okay. So then exponential function f of x equals e to the x for base e is so prevalent in the sciences that it's often referred to as the exponential function or the natural exponential function. Okay, so if we were to look at the graph, the blue graph where we have y equals 2 to the power of x, and the green graph where we have y equals 3 to the power of x, y equals e to the x is close to the green graph, but it's between the blue and the green, but it's really close to the green. So e is like approximately like 2.7. Let me see right here. So if we did like e to the power of 1, so e is like 2.71. It's similar to pi, but it's an exponential function. It comes out of like calculus, where when we take the limit of this function as n goes to infinity, it approaches this number e of a specific function. And the reason it's interesting, well, it's kind of hard for me to say it here because I'm trying to reference things from calculus. But it's just a unique function that has like unique properties that come out later down the line. In calculus is this concept called derivative. The derivative is a slope of a tangent line at a point. And so the derivative e is a unique function because it's its own derivative. The derivative of e is itself. So if you take the slope of a tangent line at any point on the function e, you're going to get back whatever that number is, right? It has these unique properties. It's kind of tricky, right? So if you ever get into calculus, you'll get to experience that and explore that a little bit deeper. You don't really need that right now. For our purposes, we just need to know how to use this function. Okay. I see the time. I'm just trying to. We're using transformations to sketch the graph. So again, we have the red, which is the general shape of the exponential function. And then in this example, we have two transformations at play. We have an inside transformation in the form of that -1. So we subtracted 1 on the inside. That should move the graph to the right by 1. And then we added 2 on the outside of the base function, which should move the entire graph up by 1. So the two transformations at play, we went right 1 and up 2. Sorry, I think I said up by 1, but it's up by 2. And then the red is the final graph, right? So we started with the blue. We're kind of tracing that point 0, 1. It should go right 1 and up 2. And then, that's one point you can kind of trace or track. And then that also means that our horizontal asymptote went up by 2. So then we have a model for exponential growth or decay. AFT equals A naught e to the KT, where AFT is your amount after time t. A naught is going to be the initial amount or your starting amount. And then K is the relative growth rate if K is positive, and it's a decay rate if K is negative. And T is our time. Let's see, what do we have? What's my time? Yeah, 3 minutes. In the year 2000, the human population of the world was approximately 6 billion people, and the annual growth rate was about 2.1%. Using the model on the previous slide, estimate the population of the world in the following years. Okay, I think let's just go ahead and do this. So let's see, AFT, A naught E to the KT. It's basically PERT. We just kind of changed the labels a little bit. So we're trying to find the future amount, the starting amount. So A naught looks like it's 6 billion. I'll put it as 6 billion. Our K, if it's 2.1%, so 0.021. So if that's the year, 2000, so then if we want 2030, that means 30 years later? So we're starting with the 6 billion e to the 0.021 times 30. Six times e 0.021 times 30. So then we get approximately, I'll say 11.27. I'll say 266 billion. And then 1990 would be 10 years earlier, so I guess that would be negative 10. Six e to the 0.021 10. So I'm just going to recall what I put in before and change the 30 to a negative 10. Hopefully my syntax is okay. 4 billion, right? Approximately. 864. I was watching a conspiracy TikTok this morning before class. It's a content creator that goes by the name of My Lunch Break, and he was talking about just trying to. He was looking at like these capitol buildings. Like when you study like a lot of cities and towns and a lot of places around the globe, the history of it, all these places, they all had like some mysterious fire that burned everything down. All of them, all the cities, they had some fire, quote unquote, that just burned everything, right? And so they're trying to say that like these capitol buildings. He's alluding to like a advanced ancient, like not even ancient, just an advanced civilization that was like it seems like it was recent. You know, I don't know, maybe a few generations back. They had like advanced technology. They built like these structures that we can't and we don't duplicate today. And it's like we were making like a lot of them are like capital buildings and things of that nature. I see the time. Let me get you guys out of here. It was interesting, and so he was looking at census reports, and just showing how like the numbers don't really make sense to what we're being told. It points towards like some kind of cataclysm or something where a lot of people died, and then if the numbers are like what the census are saying, why would you have so few people? And this was supposedly built. This structure was supposedly built at that time. It's like, why would you build a structure like this if nobody's there? Unless the structure was already there and you're just trying to cover something up that you don't want us to know. It gets deep. Like it's kind of trippy. And I was like, yo. So anyway, that content creator is called my lunch break. So he was interested, and I got him from another one that goes by the name of Jet Ski Chuck. Jet Ski Chuck is a little bit eccentric. He's just a brother, a little bit country, but the stuff that he studies is so interesting. For things like dragons to like in recent times, like mountain ranges showing how it looks like the dragon skeleton. Just all sorts of interesting things. What else? Giants, and, all sorts of crap. So it's just fun. It's just interesting. It's just interesting. Again, you got to do your own research and decide for yourself. This looks good. I think we got something similar. I'm gonna get you guys out of here because we are pretty much out of time. Okay, we're gonna have to leave that one as an exercise. You can find that one in my recordings. Are there any burning questions before we go separate ways? Let me just think as far as announcements. So again, that was an introduction to 3.1 exponential functions. This Wednesday, we'll go ahead and do the last section, which is going to be system of equations in two variables. All right. So there's homework for this already. We're going to be a little bit ahead of schedule, but again, what this does, this allows us to have 3 days of review instead of just two. All right, guys. So if there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your evening, and we'll meet back on Wednesday, same time, same place, for the next installment. All right, guys, take care. Peace. All right. Let me go ahead and do attendance.